This is the cylinder lab for Aero 302. This is by Madison Grant, Matthew Jones, Liam Mages, and Kevin McDonald. We calculated the pressure coefficient over 24 points in the wind tunnel. The standard deviation was most apparent on the back of the cylinder, and the great difference between actual and theoretical we believe is due to flow separation.
So after we were able to calculate the pressure around the surface of the cylinder from 0 to 2 pi, 2 pi being the back end of the cylinder and pi being the front end, we were able to calculate the drag coefficient around the cylinder. So you can see at pi, the coefficient of drag is kind of at its maximum at around 0.14. Meanwhile, on the top and bottom surfaces of the cylinder, at pi over 2 and 3 pi over 2, you can see that the coefficient of drag is so low that it is even negative, and that means basically that there is lift force in this case. However, the graph is not completely symmetric. As you can see, it's lower at the bottom surface of the cylinder at 3 pi over 2, and that basically means that the lifting force is greater because the pressure difference is greater on the bottom of the cylinder. Additionally, in a study that we found, the study on drag coefficient for flow past a cylinder by Malik and Kumar, we were able to compare our results to some actual data, and you can see in their graph they plotted data from 0 to 1 pi, so only over the top half of the cylinder, but you can see that the shape of the curve generally matches ours, so we can confirm our results.
So next up we are looking at Reynolds number and its effect on the coefficient of drag around the entire surface of the cylinder. So what you're seeing there on this slide here is that the right graph is a theoretical coefficient of drag over a surface versus Reynolds number, and this graph is for a sphere, not a cylinder, but the graphs follow the general same curve, and this was the most this was a reputable source from NASA, so we used that graph to compare our results. So our results are based off of 2 points that we got, one at 350 RPM and one at 600 RPM. At both of those Reynolds numbers were on the order of 10 to the 5th. So if you look on the graph to the right, that would be the region just before the sharp decrease, all the way at the right side of the graph. So we would be expecting from literature that we would have a slight negative slope as Reynolds number increases, and that is what we found. So the one thing to note is we only had 2 points to examine, and that limits our ability to be confident in our results. So that said, we'll now be moving on to flow visualization in our experiment and Struhel number.
All right, so here we have our video depicting the cylinder and the flow viz within the wind tunnel. And as you can see, the flow goes over the top of the cylinder and it oscillates between periods of attached flow and separated flow at the back. Now, if we had another stream of smoke that flowed along the bottom of the cylinder, we would see that the top flow and the bottom flow kind of switch in terms of one becomes attached along the back while the other becomes separated. In this oscillated motion, we calculated using this video to be about 14.6 hertz. Now, using that, we found the Struhel number of the flow, and it came to be 0.2994. Now, this is somewhat large for a Struhel number. They generally range between on the order of 10 to the negative 5th to 1, and this Struhel number relates to flow that is oscillating as a collective, which, as you can see, the flow remains relatively together as it oscillates throughout this period, only separating once it's very far away from the cylinder.
And in conclusion, our coefficients of pressure and drag did not vary much between the two different RPMs. The pressure matched very well with the theoretical data, except at the top and bottom, due to the difference of flow.